Hello everyone. This is Chi Jiaming, your instructor for the Deep Learning course. Let's get started with our lesson now. Hello everyone. Welcome to our Deep Learning course. Today, we're starting Chapter 5, Classic Convolutional Neural Networks 1. First, let's clarify the learning targets for this chapter. By the end, you'll master 5 key points. First, LeNet-5's network structure and code implementation. 2. AlexNet's structure and code. 3. VGG structure and code. 4. The principle and application of batch normalization. 5. The principle and skills of data augmentation. Let's start with the first classic model, LeNet-5. First, let's get to know LeNet-5. LeNet-5, proposed by Jan Lutzen in 1998. It's a classic convolutional network and the first one successfully applied to digital recognition tasks. The LeNet-5 network has a total of 7 layers, and the order is clear, starting with the input layer, then alternating convolutional layers and pooling layers, convolution pooling, followed by 2 fully connected layers, and finally the output layer. This alternating structure of convolution and pooling is the foundation of many later CNNs. Let's look at the structure diagram to understand each layer's output. The input layer is 32 multiplied by 32 pixels, then C1 first convolutional layer outputs 6 feature maps of 28 multiplied by 28. S2 first pooling layer downsamples to 6 feature maps of 14 multiplied by 14. C3 second convolutional layer outputs 16 feature maps of 10 multiplied by 10. S4 second pooling layer downsamples to 16 feature maps of 5 multiplied by 5. Then it goes to C5 fully connected 120 units, F6 fully connected 84 units, and the output layer 10 units 4 digits 0 to 9. The diagram clearly labels each layer type. Convolutional layers are marked in blue, pooling in green, and fully connected in orange, helping us visualize how data flows. Now, let's use LeNet-5 to solve a practical task, MNIST handwriting digit recognition. First, we load the dataset with Keras, from Keras. Datasets import NIST and X0, Y0, X1, Y1 and NIST load minus data equals NIST. Load data. The output 60,000, 28 tells us the training set has 60,000 samples, each a 28 multiplied by 28 grayscale image. We also visualize 10 digits, 0 to 9, with Matplotlib. Loop through each digit, take the first sample of that digit, and display it. This lets us confirm the data is correct. Next, we need to pre-process the data to fit the model. The steps are: first, reshape the image tensor, x0 equals x0. Reshape open parenthesis none, 28, 1 close parenthesis divided by 255, x1 equals x1. Reshape open parenthesis none, 28, 1 close parenthesis divided by 255, adding a channel dimension, 1 for grayscale, and normalizing pixel values to 0 to 1 by dividing by 255. Second, 1 hot encode labels. Use NP utils. 2 categorical to convert integer labels, y0, y1 to 1 hot vectors, yy0, yy1, for example, digit 5 becomes 0, 0, 0, 0, 0, 1, 0, 0, 0, 0. The output shows we have 60,000 training samples and 10,000 test samples, and the 1 hot labels are in the correct format. Now, let's write the LeNet-5 code with Keras. We use layers like conv2D, convolution, max pooling 2D, pooling, flattening, and dense, fully connected. Input layer, input, 28, 1, matches preprocessed image shape. First convolution, conv2D, 6, 5, padding equals same, activation equals ReLU, 6 kernels of 5 multiplied by 5, same padding, ReLU activation. First pooling, max pooling 2D, pool size equals 2, 2, strides equals 2, 2, 2 multiplied by 2 window, step 2. Second convolution, conv 2D, 16, 5, 5, padding equals valid, activation equals relu, 16 kernels of 5 multiplied by 5, valid padding. Second pooling, same as the first. Flatten, converts 2D feature maps to 1D vectors. Fully connected layers, dense 120, activation equals relu, dense 84, activation equals relu. Output layer, dense 10, activation equals softmax 10 units for 10 digits, softmax for probabilities. Finally, model. Summary prints the model structure. This page's diagram maps the code to the actual layer flow. Input layer convolutional, layer 1 pooling layer 1 convolutional layer 2 pooling layer 2, flattening fully connected layer 1, 120 units, fully connected layer 2, 80, 4 units, fully connected layer 3, 10 units, output. Through model. Summary, we can check each layer's output dimension and number of parameters. For example, the first convolutional layer has 156 parameters, 5 multiplied by 5 kernel multiplied by 6 plus 6 biases. This helps us confirm the model is built correctly. Finally, we compile and run the model. First, compile with model. Compile, set the loss function to categorical cross-entropy for multi-classification with one hot labels, optimizer to atom, efficient for training, and metrics to accuracy, track classification accuracy. Then train with model. Fit, use the training set, x0, yy0, train for 10 epochs, batch size 200, and validate on the test set, x1, yy1. This step lets the model learn from the MNIST data and test its generalization ability. Usually, LeNet 5 can achieve high accuracy on MNIST with this setup.